everybody. Our first speaker in this session is Christof Wetterich, quantum mechanics from classical statistics. The stage is all yours.
Thanks. Nice to be here once more. I think I take this one if that works. Tell me if the micro does not work, then I will take another one in my hand.
You need to stand a little closer to it, I think.
Okay, then I take this. Okay, so I think 4 years ago I already was telling that quantum mechanics is just a part of classical statistics and that all laws of quantum mechanics, all axioms, just follow from the standard laws how we deal with classical probabilities. Well, at this time this may have been a little bit abstract, and in the meanwhile I was looking for nice examples where you see it directly. And that is what I want to do today. So I will really show you that certain probabilistic automata, classical probabilistic systems, are identical, completely equivalent to quantum field theories for fermions. So the second is obviously a quantum theory. So let me just ask you very simple questions from the beginning. Is a model like the Turing model quantum theory? Well, it's a quantum field theory. You do not need to know what the Turing model is exactly. It's one of the simplest quantum field theories. There's fermions represented by Grassmann variables. It's Lorentz invariant. You see here's a standard kinetic term, and it has some quartic interactions. So that's a typical quantum field theory, and of course this always gives you this quantum theory, standard quantum theory for a single particle. Once you go to the one-particle state, then you just get for every quantum field theory, you get quantum theory for a single particle. Now, you can discretize that, put it on a lattice, don't really try to follow the exact formula, that's not my point, but you do it on a lattice. We define it as a Grassmann functional integral, just in the standard way. Is such a discretized Turing model still a quantum theory? Yes, of course. It has exactly the same laws. It doesn't matter if you consider discrete or continuous quantum field theories. So that's just suggestive, seems harmless. But now I will tell you that some of these interacting quantum field theories in practice, that is particular Turing model, that is the simplest one that I could find, with interactions that I want to demonstrate to you, that this is actually identical or completely equivalent to a probabilistic cellular automata. You should realize once you digest that, once you swallow that, this is quite an important step. Because obviously a probabilistic cellular automata is a classical statistical system. I will explain to you a little bit more in detail what it is, but definitely it's a classical statistical system. Quantum field theory for fermions is definitely a quantum system, and if the two are equivalent, it tells you that quantum mechanics really emerges from classical statistics, or emerge is such a general word, let me be more specific, that certain classical statistical models or models which just formulated in terms of classical probabilities, that certain models are genuine quantum models. That's the sense of this emergence, and it tells you immediately that all no-go theorems like Bell's theorem and so on, that you cannot do that, they are circumvented. There are useful theories for certain aspects, but they are not general enough, and of course some of the assumptions will be violated. A very simple assumption actually, namely that all correlations are just classical correlation functions, but I will come to that. So at the beginning you may be a bit doubtful, because you will say, well, the fermions we are used to it as real quantum objects. It has a totally antisymmetric function. You have this anti-commutator of annihilation and creation operators. If you go to function integral, you use anti-commuting Grassmann variables and the Grassmann function integral in order to formulate your theory. So a priori you would say, well, this is really very, very quantum. There is no classical analog. Now, if you go to the cellular automaton, that's just a deterministic updating of bits with a certain local structure that you have only neighboring cells influencing a given cell, but it's essentially just deterministic updating of bits. So you have this updating usually in sequential steps, so you know that's an automaton, one step after the other. At every step you prescribe how a given bit configuration is transformed to a new bit configuration. Now that's an automaton. So, and I'm telling you that these two theories are identical. So for fixed initial configuration, you will have actually just classical deterministic computing. One bit configuration goes at every time step to the next bit configuration. What I will do is probabilistic cellular automata, where the probabilistic aspect comes by a probability distribution for initial conditions. So let me give an example, and I give you an example for such an automaton which will produce exactly this discretized Turing model. It's a very simple one. So what is the rule? The rule is we have it in one space dimension, one time dimension. So x are just discrete lattice side, and also the time steps are discrete. And then we have two colors of bits. We have red bits and green bits. And we have two sorts of bits, right-moving bits and left-moving bits. So altogether we have four sorts, four different species of bits. The red and the green left and right movers. And now I give you the rule. At each time step, the configuration of the right movers moves one position to the right, and the configuration of the left movers moves one position to the left. This will give you a free theory, actually also already a free relativistic quantum field theory. But now you want to have interactions, and the interactions is if two single particles meet, then colors are exchanged. I give you it a little bit to just visualize it. For example, here a red and a green single particle meet, then the red particle becomes green and the green particle becomes red. Or here, for example, two red particles meet, then the colors are exchanged, both continuous as green particles, and it's very easy, and you see it looks already a little bit like Feynman diagrams with loops and so on, but it's a very simple cellular automata, nothing particular. You can now already on this level, even without going to probabilistic theory, implement certain ideas of quantum field theory. For example, you can look for possible ground states or vacuum states. Typically here just half your states, where at every side of the lattice you have exactly two particles out of the four, and you see you have already different ground states. For example, here you have a ground state where on this level you have only green particles, then in the next step these are only red particles. Here you have mixed states, the left movers are green, the right movers are red. And you see that these ground states, they break the symmetries. There's of course the whole action has a symmetry, red goes to green, and it's broken in two different ways. So you see already the notion of spontaneous symmetry breaking. Ground state has less symmetry. And then you get even solitons, which are one of the characteristic features of these Turing models that they have for solitons. Well, if you have now a line, if you have a defect, so on this black point here, you have no right mover. So this if you have no right movers, this just goes on. Or you have two right movers, one red and one green. They also do not scatter. So on this line, you just cross this line without changing the color. Why is it a soliton? You will not see it immediately, but if I color this one, you see that you have one sort of vacuum here, the same one here, but then you have the other vacuum here, and the soliton line just separates two different vacua. So that's a typical example of a soliton being a defect if you have spontaneous symmetry breaking in a vacuum. So these simple things, they are already even present for a deterministic automaton, but it tells you already that these things look really close to the Turing model. And it's of course not an accident, because I constructed this automaton such that it will at the end give this Turing model. Now let's go to a probability distribution for initial conditions. So up to now I think I'm completely in line with Gerard with his automata. I think for me the probabilistic aspects will be very crucial in order to really extract a full quantum field theory out of it, and a full quantum theory, and you will see how it is. It's a very harmless probabilistic setting. You just give a probability distribution for initial conditions. That's all. And once you do that, I will show that this automaton is equivalent to this particular Turing model. So, first of all, we have now to match these things. Fermions and classical bits, they're not so different, because after all you can characterize any fermionic state in a multi-particle fermionic system by occupation numbers. Occupation numbers are 1 or 0. Well, these are bits. So forget that fermions are completely quantum objects. Fermions are just bits. They can take in an appropriate basis, occupation number basis. They just have 1 and 0s, and every fermion configuration in occupation number basis is just a bit configuration. So here we are already very close to the cellular automata, because in the cellular automaton you just evolve bit configurations, and for a fermionic quantum field theory the time evolution just evolves bit configurations. So classical bits and fermions actually span the same Hilbert space. You can also formulate it as Ising spins. Ising spins are then of course just 2 times the occupation number minus 1, so S has the numbers plus or minus 1, so you can also say fermionic models, fermionic quantum field theories are just particular generalized Ising models, and any bit configuration gives you now a many-body state of fermions. Now probabilities, that's not very complicated. You say I have a given state rho bar, a given bit configuration rho bar, and at the initial time I just say, well, I give a probability p rho bar at the initial time. So for every possible configuration I give a probability that gives me a probability distribution. Now the evolution for such an automaton is particularly simple, because if the configuration rho bar at t in is mapped to a configuration tau at some later time t, then by the cellular automaton processing, then at the time t the probability to find tau is of course exactly equal to the probability to find the configuration from which it originates at t in. So the probabilities, since you have a deterministic time evolution, the probabilities just get transported. So if you have a probability of 1/3 for a particular configuration at t in, then you just compute what this configuration becomes later through the cellular automaton process at some later t, and then this evolved configuration will just again have the same probability 1/3. So very trivial observation, very trivial rule. Now, to come closer to quantum mechanics, we do something very simple. We express the probabilities in terms of probability amplitudes. And it's not complicated. Here we have actually to do just with real wave functions. We can introduce a complex structure later. And for real wave functions, you just have the property that the square of these wave functions, so the wave functions live now in configuration number space or in the space of bit sequences. The square of each component just gives you the probability for this configuration. Couldn't be simpler. So that's the rule. And you see these wave functions are very useful if you want to do dynamics, because probabilities, they have to have the sum rule that the sum is 1 and they have to be positive. That's all a bit complicated in a general sense to implement. Once you go to the wave function, it becomes very simple. It's a unit vector, and every dynamics will just be a rotation of this unit vector, as it is in quantum mechanics.
It's no more classical. It's no more classical from there.
Call it as you want. It's classical probabilistic. You can call it whatever you want. I just tell you, I define a wave function for my cellular automaton. I'm not saying it's different from quantum, because actually the same wave function is the wave function that tells you what happens in the fermionic system and what happens for the cellular automaton. They live in the same Hilbert space. And if they have the same evolution, that's actually what one shows at the end. If both of these wave functions have the same evolution at every time step, then the theories are just identical. Okay, so if you compare to deterministic cellular automata, then you would have just a given initial state, a delta function here, a sharp state. But probabilistic is very simple. You go to arbitrary wave functions. That's the only step that you do. And that gives already a lot of possibilities, because now you can have derivatives of the wave function, new operators. You can find a continuum limit, which is very, very important in this game. For a deterministic cellular automaton, no continuum limit exists. And of course you get already the basic features of quantum theory in a very straightforward way, namely the so-called particle-wave duality. It's a very cheap thing. The particle aspects are the discrete observables, the bits. They take ones and zero values. What is the wave function? What is the wave aspect? Well, the wave aspect is just a continuous probabilistic information that you put into the wave function. So the wave function is not something directly measurable. The wave function has a similar status as a probability distribution. It's just a probability amplitude. But this is a continuous function. So that's where the wave aspects come. And it will be a true wave if you have appropriate dynamics, as it is in this case actually. So now we have to speak about evolution. Evolution is again very simple. You want now to derive an evolution law that encodes this cellular automaton updating, and you do it by saying that the wave function at t plus epsilon, epsilon is the size of the time step, that this is a so-called step evolution operator that multiplies the wave function. So in components it is this function here. And this step evolution operator for the cellular automaton has actually a very simple structure. It's essentially delta function, and if you just insert it, you find that the probabilities are updated according to the rule for the cellular automaton. Now, if you want to see it a bit more visually, this step evolution operator for automata, for classical automata, these are just so-called unique jump matrices. They have in every row and in every column one element 1, or minus 1, that actually does not matter, and the rest is 0. And that tells you that every configuration is updated to precisely one new configuration, and in this case it's also an invertible operation. So it's very simple, and you would say, well, all very nice. Can we see a bit more about fermions? There's a whole general map that I developed actually, how to map generalized Ising models to fermion models that goes in arbitrary dimensions and so on. I will not show you that. I will show you something that looks much easier. Namely, I will just express this step evolution operator, this unique jump matrix in terms of annihilation and creation operators for fermions. So we have the standard A and A dagger, and I will express it in terms of these operators. Well, the first thing I do is you can factorize the step evolution operator into a free part and an interaction part. That's not very surprising. The free part tells you all right movers move to the right, all left movers move to the left. And then the interaction part tells you if two single particles meet at a place, then the colors are exchanged. So obviously the interaction part is local, so it happens at every point on this lattice. Whenever two single particles meet, they exchange color. So that has a very simple structure, and the free step evolution operator is of course also a very simple structure. It just moves particles to the right and to the left. So now let's go to the fermionic creation and annihilation operators. What do you find? Well, the first is the interaction part. It actually can be represented, it's exactly e to the I pi over 2, and then you have a typical fermionic interaction. You see left and right. If you have a left mover and a right mover with different colors, they will exchange color and so on and so forth. So it's easy to understand that you need to annihilate two particles and to create two other ones with the corresponding colors. So you have a very simple interaction part. Then you have the propagating part that almost looks already like a derivative, but there is still some normal ordering of operators in front of it. It's this normal ordering that guarantees you this unique jump property. But already you see it's a...
Christof, does the imaginary I cancel every time?
I started without an I, and it's just an identity that if you take this operator here and you apply it to arbitrary states, it will give you. You can just expand that, let it work on states. It's a mathematical identity that this step evolution operator for the interaction that has only real ones or minus ones has this form. So that's where the I comes. It's not a surprise, because obviously the step evolution operator for an automaton preserves information. So it has to be presented as, in general, could be an orthogonal matrix, but it can also be a unitary matrix. And we may discuss the complex structure a little bit later. For the moment, just take it's an identity. Here you see, for example, you do not have an I in this part, but you also realize that this is almost a derivative, and it's actually I times the derivative that will be a Hermitian operator. So you can of course define Hamiltonian. That's pretty trivial. In Gerard does that also very often. You have an evolution operator. You can immediately write it in this form. This defines you what is your Hamiltonian. And then, of course, once you have this Hamiltonian, where you assume that it does not change between two time steps, then, of course, you can also write your evolution just directly as a continuous evolution with a unitary evolution operator. You get a Schrödinger equation, and this Schrödinger equation has the property that for all discrete time steps, it produces exactly the result of the cellular automaton. Now you should of course imagine that we go at the end to the continuum limit, where we have billions of time steps, and where you will not resolve anymore the individual time step. So that's the idea of any continuum limit in quantum field theory. You discretize time, but the time steps get to zero when you do your continuum limit. In the continuum limit, the Hamiltonian gets even simpler. That's what you know from Feynman's integrals in a certain sense. It just uses the same trick. In the continuum limit, you can just write your Hamiltonian as a free Hamiltonian plus an interaction Hamiltonian plus some correction, and this correction vanishes when the time step goes to 0. Obviously, this requires smoothness properties of the wave function. So the wave function should not change very much for an individual time step or for two neighboring places, but this is exactly what you can do with your probabilistic cellular automata. And now you see you just get in the continuum limit a standard Hamiltonian for the propagation of left-handed and right-handed fermions, and you get an interaction term that is also Hermitian for a quartic interaction. So it's just mathematics, simple mathematics. We had this particular automaton. We expressed it in terms of annihilation and creation operators, and you see in the continuum limit, this is actually precisely the Hamiltonian for this Turing model. Question is, of course, is the naive continuum limit justified? Just taking epsilon to 0? That's not such a simple question. That needs renormalization group and things like that. As we know from lattice gauge theories, the continuum limit is not completely trivial, but you see that at least the naive continuum limit gives you the continuum Turing model, and actually the discrete model, you can of course, you do not need to take the continuum limit. The discrete model is one-to-one equivalent to this discretized Turing model. So I told you that there's a general bit fermion map. This is just based on the fact that the Hilbert spaces are the same, occupation numbers are bits. And then the only thing in order to show that you have to show is that the evolution operators are the same. If the space is the same, the evolution operators are the same, then the two models are just two different pictures of the same reality. And then, of course, every operator that you can construct in one, you can construct in the other. So that's, I'm almost going to the end. You have a general, actually a much more general quantum formalism for classical statistics that I did not tell you. Just as Feynman produces the wave function from the Feynman functional integral from the e to the is, you can just use the same tricks with e to the minus s for a classical statistical theory. It produces you the classical wave function, and you can do one-to-one translate all this formalism of operators and so on from the functional integral to the transport from one time hypersurface to the next one. Actually, statistical physicists know that. That's called the transfer matrix formalism, and you have already transfer matrix. Matrices do not commute in general. And the only thing I'm doing is telling you that this transfer matrix formalism is in a sense the Heisenberg picture, and now you can have an equivalence Schrödinger picture where you also have wave functions on which these transfer matrices act, and that is these classical wave functions. And then you get all quantum rules, Born's rule, and so on and so forth. You just get it from the laws of classical probabilities because you have, of course, the classical expectation values are well defined. Then you compare with the quantum expectation values that you get by switching it between wave functions, and you see it's just the same expression. So all quantum rules actually follow from classical statistics. So that's at least what I have shown you today for these particular models. There is a direct isomorphism between a probabilistic cellular automaton that you can also represent as a type of Ising model and quantum mechanics or a many-body system for fermions. All expectation values of all observables, all correlations, it's all the same. The time evolution is the same, so these two models are really the same. And, well, the consequences, I think, either you tell me I did something wrong, mathematics is wrong, or you just have an example where quantum mechanics is described by a classical statistical system, and you avoid really all sorts of no-go theorems, and I will just explain as a last thing how to avoid it for the observables of position and momentum. Position observable is very easy to implement since we have the bits at given positions. Now, what is the momentum observable? Obviously, if you have fermionic quantum field theory, the momentum observable is a very important observable. It's a conserved quantity. For free theories, just tells you how particles propagate. So now you can just translate it, ask what is it actually for this probabilistic cellular automata? What is the momentum observable? It's of course the same operator as for the fermionic system, and if you ask what does this operator measure, it actually measures the eigenvalues of this operator. They tell you the periodicity of the wave function. So that's an important point. There are observables or operators that do not have a fixed value in any one of the bit configurations. They just measure a property of a probability distribution or a wave function, namely that it is periodic, and it tells you what is the period. So these are statistical observables. We know them actually. Temperature is a similar observable. We observe temperature. That's just a property of probability distribution. The temperature does not have a fixed value in any particular state of molecules with given positions and momenta. So you have these simple statistical observables, and they do not have a fixed value in any one of the bit configurations. And then there is no classical correlation function between momentum and positions, because otherwise both observables would have to have a fixed value for every configuration. That's a very simple way how Bell's theorem is circumvented. Simply, there is no classical correlation functions for this pair of operators. I think I conclude. I do not have to say too much. I hope that actually this equivalence will at the end also be useful to solve problems. You know, if you have an automaton representation for quantum field theory, you can of course simulate it in this way. That is not for this purpose, for this conference, my purpose here. For this conference, it's just a simple statement that yes, there exist classical probabilistic systems that are fully equivalent in all respects to a quantum system, and therefore you do not need new axioms for quantum theory in general. They all follow from the classical probabilities once you look at things in a correct way. In a sense, my aim is not to replace quantum theory. I believe that this is the theory of our world, but to demystify a little bit. There's too much mystification, too much things just calculate and swallow, and after all, things are much simpler, just classical probabilities. Thank you.
Thank you, Christof. Unfortunately, we have only about 2 minutes. So, Gerard.
Of course, I subscribe to the philosophy, as you know, but there's a very important step that you have not yet made, and that's that in quantum physics, wave functions spread. And your wave functions, nowhere I see any sign that they will spread. I think they don't in general. Okay. Unless you do something more important and more complicated.
It's a very good question, Gerard. Of course, I'm worried about that as well. In this type of two-dimensional system, it's very simple, one-wave functions do not spread. That's actually a property of this Turing model. And that is a property of the Turing model because it's a massless model. So now, of course, you can implement as well massive models. I know how to do that. And let me tell you how you do that. In my view, in the simplest way, you want to have masses, and you also want to formulate things in 4 dimensions, which is not completely as trivial as in 2 dimensions. So what I did this summer, actually, just to solve that, I wrote down a 4-dimensional automaton for spinor gravity. So it has then the action has 32 spinor fields, but it has local Lorentz symmetry, and in the continuum limit it has diffeomorphism symmetry. So that still has only massless particles, but as soon as you get expectation values of spinor bilinears, that would account for the vierbein or for the metric, then you can actually get masses. So masses arise through expectation values of spinor bilinears, just as you can have it in the Gauss-Neveu or Thirring models. I agree, this is, I know the way to go, it's not yet done.
I think we have time for one very quick question and quick answer, please.
The question is quick, the answer is up to you. Your answer was quite long. If I remember well, the Thirring model is dual to a sine-Gordon model, which is sine-Gordon. It's a discovery of Coulomb, right? But it's a bosonic model. Is this important for you? So it's 2-dimension, dual to a bosonic model, not spreading. There's too many.
Quick answer. So Thirring models are actually also equivalent to Gauss-Neveu models. That's trivial, but there are also bosonic versions. This is not what I have used. You see, there are in 2 dimensions very particular maps between bosonic and fermionic variables. The map that I'm using is a much more general map, and it's not equivalent to that. The map I'm using is extremely simple. You see, I'm not using solitons for the map or something like that. I'll just say a bit is a fermion, and that's it. That's the map.
Let us thank Christof again.